Wide bandgap materials like SiC and GaN are really changing the game in power electronics, helping devices become faster, smaller, and way more efficient. But what does wide bandgap actually mean? To understand that, let's first take a quick step back and look at the Bohr model of the atom, just to get a feel for how energy levels work. So as you know, an atom has a nucleus in the center and electrons move around it in specific orbits or shell. Take silicon for example. It has an atomic number of 14, which means it has 14 protons in its nucleus. And because it's a neutral atom, like all elements on the periodic table in their natural state, it also has 14 electrons to balance out those protons. Let's distribute these 14 electrons in their energy levels around the nucleus. The first energy level can hold up to 2 electrons, so we start by placing 2 there. And that shell now is full. Next, we move to the second energy level, which can hold up to 8 electrons. So we add 8 more. That gives us a total of 10 electrons so far. And since silicon has 14 electrons, so we have got 4 left. Those last 4 electrons go into the third energy level, which becomes the outermost shell. The outermost shell is called the valence band, and the 4 electrons sitting there are called valence electrons. Well, now there is another energy level above that. It's normally not occupied by any electrons, and we call that the conduction band. For an electron to become conductive, it needs to gain enough energy to jump from the valence band up to the conduction band. Once it makes that jump, it's free to move, and that's how it can conduct electricity. But here is the thing. Between the valence band and the conduction band, there is this gap which called the band gap, or sometimes we call it forbidden gap, because electrons cannot exist in that space. They either stay below it or jump completely over it. If we look at the band theory, you will notice the clear difference in band gaps between conductors, semiconductors, and insulators. Once again, the valence electrons sit in the yellow area, that's the valence band, and the red area above is the conduction band. The gap between them is what we call the band gap. For instance, in conductors, the band gap is basically 0. As you can see here, the valence band and the conduction band actually overlap. So electrons in the valence band are already in the conduction band. There is no gap to cross, which means the outermost electrons are free to move and conduct electricity right away. Now, in insulators, the band gap is very large. That means there are almost no free electrons available to carry current. In other words, the electrons in the valence band don't have enough energy to jump into the conduction band. Since they cannot make that jump, so they simply stay stuck, and that's why insulators do not conduct electricity. While in semiconductors, things are different. The band gap is much smaller, so electrons only need a little bit of energy to make the jump from the valence band to the conduction band. This energy can come from heat. Even just slightly above absolute zero can be enough. Take silicon for example. It has a band gap of about 1.1 electron volts. With a little thermal energy, some electrons can gain enough energy to jump into the conduction band. Once they are there, they are free to move, and if we apply a voltage or electric field, they can carry current. Now you might be wondering, where do wide band gap semiconductor fit into all of this? Well, wide band gap materials simply have a larger band gap than traditional semiconductors like silicon. For example, silicon carbide has a band gap of around 3.3 electron volts, and gallium nitride is slightly higher with a band gap of about 3.4 electron volts. So compared to silicons of 1.1 electron volts, that's a big jump, and it opens up some major advantages, like that wide band gap materials can handle higher voltages without breaking down, making them ideal for high power applications. They lose less energy as heat, which improve energy efficiency in power electronics. And because of their wider band gap, these materials can operate at much higher temperatures without degrading. Also, wide band gap devices like SiC and GaN can switch on and off much faster, which means we can run things at higher frequencies and make the design smaller and more efficient with less cooling requirements. So that's a quick overview of what a band gap is and how energy levels work and why some materials conduct electricity while others don't. If you found this video helpful, make sure to like and subscribe. Thanks for watching and see you in the next video.